Good afternoon. I would like to thank everyone who will be watching this right now, and I would like to thank all lecturers at the Department of Electrical Engineering in Obafemi University who have actually contributed to the learning and the understanding of this course. And some of them which I would like to mention in this video is number one, Mr. Olayobola and Dr. A. and Dr. Awe, who has taught us this course. So the main aim of doing this video is not for you to ditch your class for this video. It's just to at least bring a bridge between what you learned from your lecturers, professors, and at the same time explain further so that you will have a deeper understanding of everything in signals and systems. This course is I want to tell you that this course is one of the most simplest courses in engineering field, but it only needs some little mathematical background. And some of the mathematical background that it needs is, number one, it needs an understanding of linear algebra, it needs an understanding of calculus and pre-calculus very well. And so now let's get into the real show, which is signals and systems. Now, what is signals? The course is signals and systems. What is really signals? Signals, as written here, the formal definition I'm going to be using here is signal is a function representing a physical quantity or variable which may contain information or a nature of a process. And if you are a theorist who is listening to me, you know that a signal is a function that maps a domain into a range, and the domain oftentimes is always time or space, and the range is always physical, any physical thing that can be measured. Now, enough of all this definition, let me break it down to you. What signal is? Remember your Ohm's law. Remember your Ohm's law. In your Ohm's law states that provided temperature is kept constant, the current passing through a metallic conductor is directly proportional to its voltage. Right? Now, your Ohm's law is simply, I have a cell here, which is a battery source, then go to, let me say, a bulb. Don't mind my brain. Going to a bulb. Now, this is a voltage source. Now, if you have a voltage source, and this is your bulb. So, this is your bulb. Now, one thing you will understand is, if I have a small battery and I connect it to a bulb, the next thing I'm likely to see is that this bulb is going to be lit up with what? With light. We say, yeah, this bulb has been lit up. What actually happens is that the voltage source produces, after this whole circuit is complete, produces something we can call what I, which is a current. Now, this I cannot be seen, isn't it? Now, that I is actually the signal the voltage source sent to the bulb to produce the light, to light up the bulb. So your signal is actually, your signal is actually a function that maps a domain into a range, and as this definition has also told you that a signal is a function of a physical quantity or variable which contain information or a nature of the process. Now, the nature of this process is that you must have light lit up in this bulb after we are connected it to the voltage. But something we don't see here is that the signal which is here, the signal in between B and bulb, what is connecting the voltage source and the bulb is actually a signal which we commonly call what? Current. So from here, I'm going to be telling you more about signals, and we are going to be moving to the different types of signals that we have. Okay, now this is types of signals. One of the major types of signals that we have is periodic and aperiodic signal. What is meant by periodic signal? Any signal which a time shift in that signal produce that same signal is actually periodic in nature. What I mean is a periodic signal can be a continuous or a discrete signal or a discrete time signal that has the property that there is a positive value of t for which x of t is equal to x of t plus nt. What I mean is this: if the signal is actually shifted by say let's say t, you will still produce the same thing as what x of t. That is, any signal that if I can write x of t and x of t, if I write x of t is the same thing as me writing x of t plus, let's say 2 pi plus k. This is going to be the same thing. Why? Because actually I only shifted this through what? Through 2 pi. Through 2 pi k, and that 2 pi k can actually, or I should say x into bracket t plus 2 pi of t. This I have actually shifted, even though I have actually created a time shift for this signal, I will still produce this same former signal back. Any signal that will base this is actually called what? A periodic signal. Now, what is an aperiodic signal? An aperiodic signal is a signal that is not periodic in nature. That is a signal in which if it experiences a time shift, will not produce the former signal which was shifted. That is actually what we call a non-periodic signal. Now, I will be giving some few examples in a bit, and those examples will make us understand actually how to classify whether a signal is whether a signal is periodic or is aperiodic. Okay, now here I'm going to be giving 3 examples for you to classify them as whether they are periodic signal or aperiodic signal. So right here I have x of t is equal to cos into bracket t plus pi over 4, and as you can see this question here, how are we going to classify whether it is periodic or is an aperiodic signal? First, you should know something. A periodic signal must have a rational number for its period, while an aperiodic signal will have an irrational number when you get its period. Now let's move on and let's try this out. Now look at this. If I have x of t is equal to cos into bracket t plus pi over 4, I can actually make this pi over 4 can actually be my omega. So I can actually compare it with x of t is equal to cos into bracket t plus, let's say, omega. So here I can say my omega is equal to what? Pi over 4. So that my period is going to be given as what? 2 pi over omega, which is going to be 2 pi over pi over 4. Pi cancel pi, I end up having what? 2 multiplied by what? 4 over 1. Hence, this is what? 8 seconds. Hence, we can say this signal is actually what? A periodic signal. Now here to the second example. So we can say let x of t equals cos pi over 3t plus sine pi over 4t. Now, in this example is quite different from the previous one in that the previous one we only have one trigonometric function representing our signal, right? But in this new example, we have two trigonometric functions as our signal. Now, to get the signal is going to be very, very simple. What we are going to do is, number one, we'll break this signal into 2, so that it looks like just the previous example. So I can say let x1 of t equals cos bracket pi over 3t, and x2 of t equals sine bracket pi over 4t. So therefore our x of t will be equal to x1 of t plus x2 of t. So now I can actually get the period of this first signal separately, and actually get this period of this second signal separately. Then thereafter I will now find a general period for these two separate signals, for these two trigonometric functions, which is the whole signal that was given initially. So these are how we go about it. Our x1 of t can be compared to we having what? Cos into bracket wt plus 5, as I said earlier. So here we can say it is what? x1 of t is cos pi over 3t. But in this case, there is no phase. So we can actually now say this is x1 of t. Let me call this xn. Generally, this is xn. Now, in that case, we can say our omega is equal to pi over 3. From here, if you compare this to this, you can say our omega is pi over 3. Moving on, we can say our t, let's call this t1, is going to be 2 pi over what? Over omega, which is 2 pi over pi over 3. Pi cancel pi. Hence, we have t1 to be let's put it this way. Let's do the same to x2. Xn at the same time, xn at the same time can also be in this form if it is in trigonometry. Sine wt plus 5. So in this case, we will compare our xn of t in this case with what? x2 of t, which is sine bracket pi over 4t. You can actually get our omega to be equal to pi over 4. So continuing from here, we can get t to be what? Our t2 to be 2 pi over pi over 4. Hence, we will do this very well, we'll get 8 seconds. But this is 6 seconds, this is 8 seconds. And the signal that we are given is, let me say, the sum of these two separate signals, these two signals that are actually separated. How we go about that is, let's find the ratio of T1 to T2. We'll say the ratio of T1 to T2 is equal to what? Is equal to 6 over 8. So if the ratio of T1 to T2 is 6 over 8, I can break it into simplest terms and say 2 goes here 3, 2 goes here 4. So I have 3 over 4. I can say T1 over T2 is equal to 3 over 4. So I can cross multiply and get this to 3T1 is equal to 4T2. Now, which is going to be equal to my T0, which is going to be T0, where T0 is going to represent the general period for these two signals. So in that case, let me finally finish it here. What we are now going to do is, let's just pick one out of that equality. T0 is what? 4T2, which is 4 times, what's my T2? My T2 is, okay, 3T2 multiplied by 4T1. So let me just pick this 4T1. My T1 is initially was 6, which is going to be 4 times 6, 24 seconds. Hence, the period of this whole of these two signals is actually 24 seconds. Now, we have the third signal. The third signal is looking just more like the second signal, but we'll see the difference in each. Now, let's do the same thing with the second signal. We say let x1 of t equals what? Cos t. Hence, from this case, we can get our omega directly to equals to 1. Then we can say t, our omega 1. Then t1 in this case is going to be 2 pi over omega 1, which is going to be 2 pi over 1, which is 2 pi seconds. Now, our x2 is going to be sine root 2t. Hence, this is going to be omega 2, which is going to be what? Root 2. And t2 is going to be 2 pi over omega 2. And we have 2 pi over root 2. Now, 2 pi over root 2 is more like root 2 pi seconds. Now, you remember when I wanted to start this video, I actually told you that for a signal to be periodic, it must have a rational number at its period. It must not have an irrational number. Now, root 2 is an irrational number, you can judge that for yourself. So, because root 2 is an irrational number, despite the fact that we have this to be what? To be a rational number. The first part of the signal to be a rational number. This whole signal altogether, x of t, will not be x of t, because x2 of t gave us an irrational period. X of t generally will be an aperiodic signal. Aperiodic signal. Hence, that simply now means that whenever you have a rational period, you have a rational number as your period, then you have a periodic signal. And a rational number as your period, then you have an aperiodic signal. So this will be the end. I will do another miscellaneous example on periodic signal, and that will be the end of classifying our signal, whether it's periodic or aperiodic signal. Okay, now I'm going to be doing miscellaneous example on the periodic and aperiodic signal, because most of the signals that I've given you are actually, most of the signals we have done earlier are actually continuous time signal. But don't worry, we'll still get to when we classify between what is really the difference between this bracket and this other bracket. What is the difference between when I write x of t like this and when I write x into bracket n like this? Now, the quick a quick difference I can tell you is when you have something like this, when you have this kind of, or when you have this kind of bracket, it's actually telling you this signal is actually a continuous time signal. While when you have this kind of bracket, this is telling you that this is a discrete time signal. We'll get to the classification of that in a jiffy. But first, let's solve this as a miscellaneous example here. I have x of n is equal to ej pi over 4 of n. Now, the period, let me quickly state this. The period, I will calculate period for a discrete time signal such as this is actually 2 pi over something that looks like omega, or it looks like the symbol for our ohms. So this is how we calculate what the period. And we don't call it C in this case, we call it N. We don't call it T in discrete time signal, we call it N. You know, under the one we've done before, I actually do write first. T is equal to 2 pi over omega. This is because this is actually meant for continuous time signal, and this is actually meant for discrete time signal. So now let's move on. My x of after letter n, I can compare if it is given as what ej bracket pi over 4 of n. I can compare this to what generally given the x of n generally is given as what ej. This is going to be omega 0 of what? Of small letter n. Now, this, I'm going to compare this side with this side. If I compare this side to this side, I have E complex number, ohm naught, and is equals to what? E raised to j bracket pi over 4 of n. Now, I can see where omega is standing is where what pi over 4 is standing. So, my omega as in this case is what? Pi over 4. So, I'm left with an option to calculate what my n. So, my n in this case is going to be given as well 2 pi over pi over 4. Hence, I have what? I have it to what? 8. So, therefore, the discrete time signal, the period of this discrete time signal is actually 8 seconds. Now, let's move to the second one. So, the second one here is given as x into bracket n of cos into bracket pi over 3 of n plus sine into bracket pi over 4 of n. How we do this is just the same way we did in the continuous time signal. First, break it down into one signal. Now, like this, x1 bracket n, let x1 bracket n equals cos into bracket pi over 3n. Then x2 bracket n equals sine pi over 3n. You see this? So that my x of n is equal to what? x1 of n plus x2 of n. So if we have this, then now let me compare this x1 with this. I can actually write my xn, the same xn that I have here. I can actually write xn and also the word cos into the omega naught of n. In the same way, similarly, if the signal is actually a sinusoidal signal, a sinusoidal discrete signal, a sinusoidal discrete signal, I can also write it as well, sine omega naught of n. So now, I can compare this, let me call this one, let me call this one too. Now, I can compare this with what? The cos part of my signal. So, comparing, I have x1 of n, which is equal to cos pi over 3n. Then I have xn, which is just like the general or generalized discrete signal if it is in cosine. If it is in cosine 10, it's going to be cos omega naught or what of n. Now you see my omega naught is standing where pi over 3 here is standing. Hence they are equivalent. Omega naught is equal to pi over 3. Now I will keep this. Let's do this like this. I'll keep this. So this is going to be my omega naught of pi over 3. Then I can now get. Now using this same formula, I can get my capital letter n1. My n1 is now going to be what? 2 pi over pi over 3 x. This is what? 6. In the same way, I can move on to get my x2 of n. My x2 of n is given as sine into bracket pi over 3 of n. And generally, I can write my xn of 2 as what? Sine omega naught of n. So in this case, where omega is standing is where my we have pi over 4 instead. Pi over 4, and here we have pi over 4. So here I'm going to have my omega naught is equal to pi over 4. Hence, I can say that my n1, my n2 now is going to be 2 pi over pi over 4, which is what? 8 seconds. This is 6 seconds for this, then 8 seconds for this. So now, let's move on to this. Now, how, this is a whole signal, but I've broken it down to what? I've broken it down to x1, x2 of n. Now, I need to find a general period for what? n1, n2, because they are a sum, they are sum that is given as my signal. So in this case, I'm now going to find a ratio first. n1 over n2, just the same way we did at the continuous time signal. n1 over n2 is 6 over 8. If I break it down, this is going to give me what? This is going to give me 3, this is going to give me 4. So I have n1 over n2, which is going to be what? 3 over 4. But I must find a period that can represent this x of n. Since I've gotten whole numbers and I've gotten a rational number, that means the period of this signal do exist, so it's a periodic signal. From here, I can now say this is going to be 4n1 is equal to 3n2. Now let everything equals to what? N naught. Where n naught is the period is the general period for what? X of n, not for x1 of n, not for x2 of n. So in this case, I can say my n naught is equal to 3n2. What did I get for my n2 before? I got for my n2 8 seconds. So I can say 3 times 8, which is going to be 24. So this is going to be where I'm going to be stopping for what? For periodic, classifying our signal as periodic or aperiodic signal. Okay, now the types of signal continues. Now a quick recap on periodic and aperiodic signal. We have talked about periodic signal and we talked about aperiodic signal. Now, and I've given an example on that. Now, right now, I want to talk about something which actually popped up while I was trying to explain periodic and aperiodic signal, which is actually discrete time signal and continuous time signal. See, a discrete time signal are signals that only occupy a spectrum at a defined interval. That is what I'm saying is a discrete signal can be like this x of n, and we can write it in such a way that we can have something like this. Let me just use a simple signal like our impulse function, like delta into bracket, delta close bracket n minus, delta into bracket n minus, let me say k, close bracket like this. Sum from infinity to minus infinity, or we can even say from n to minus infinity. This kind of signal are called discrete signal. These are signals that come to spectrum, and they only take that spectrum at equal interval. A graph to actually show that is, if I have a discrete, this is a kind of discrete signal. Look at this. I have this. I have this. I have this. You can see, and I call this maybe 1, 2, 3, 4. This is a discrete signal because they take the signal and what are in steps. 1, 2, 3. They occupy a defined spectrum at equal intervals. So you can see 1 is standing here, 1 is standing here, 2 is standing here, 3 is standing here, 4 is standing here. There is no signal at 1.5. There is no signal at 1.8. There is no signal at 2.8 in this whole in the graph of this signal. That shows that this kind of signal is what they are called discrete time signal. Now, continuous time signal can take on any value within any time or within any period or any time given, any time range that is given. That is, your continuous time signal is Your continuous time signal can be like this. It can be like this. So at 1, there is going to be a value for it. Even at 1.5, let's say this case is 1.5, there is going to be a value. At 2, there is going to be a value. There is always a value at each time. So it can take on any range of values. Any range of values at any interval, at any time interval. That is why it is called continuous time signal. And oftentimes is always represented as what x of t or x or I should call it y into bracket t. It's always a function of time. Why this is a function of n? Because where that n is actually defining the steps. So moving on, I'll move on to deterministic, monistic, or deterministic signal or random signal. Random signal. Now there is a difference between these two. Now, in a deterministic signal is a signal that can actually be given a value. Is a signal that can be defined, that is well defined. That's the way to explain deterministic signal. Where random signal are oftentimes they are always noise in our system. In any physical or realizable system, they are always noise. So random signals are always signals that occupy. They are not defined. They are not well defined. So they are a mixture of different signals, and oftentimes they are always a source of noise in our system. Okay, now another type of signal that we often encounter in signal system is even and odd signal. What is an even signal? Even signal are signals that are always identical with their time reversal. That is, if you take the time reversal of that signal, you will get the same thing. You will get the original signal, but that is actually an even signal. That is, what we are saying is, if I have x of t, now my x of t is equal to what? X into bracket minus t. That is, a time reversal of this gives me this. If this is the original signal, x of t is equal to x into bracket minus t. If this is true, then we have an even signal because they are always identical to meet their time reversal. Now, what is an odd signal? An odd signal are signals that are not always identical with their time reversal. Oftentimes, they are always like the opposite of the original signal. For an example, let me just put this that this is, let me call all of this, let me call it even signal. This equation actually shows that even signal. For odd signal, what we have is x of t is equal to minus x into bracket minus t. That is, if you take this is going to be x into bracket minus t, which is equal to what? Minus x into bracket t. Now, that is in an odd signal, what you have is, if you take a time reversal of the original signal x of t, what you will end up getting is what? Minus 1, that is a negative amplitude, like the opposite of the amplitude of what you have in your original signal. That's what you have as your odd signal. Now let's talk about real signals, real value signals, real signals, and let's call it complex signals. A real value signal, real signals are always signals that are specifically defined within the range of what? Real numbers. That is, signals whose domain, I have defined at the start of this video. I defined signals for you that signals actually maps from a domain towards to a codomain. In these real signals, are always signals that let me define it as that maps from real signal to another real signal. These they are called real signal. They are specified in real numbers. Unlike complex signals, let me say majorly most of our signals are, let me also say is that in most systems, what you always see is oftentimes a complex signal. Reason being that complex signals are easy to achieve because most of our signals are always is either they are cosine or sine and they are sinusoidal. So in this case, complex signals are always signals represented in this form. You must have seen this while we are doing periodic and aperiodic signals. Complex signals can be represented with this is an angular form of representing a complex signal. And even your sine signal, your sine WT is also a complex signal. It can be taken towards a complex signal. So a complex signal can be represented by a complex field. Now, I will create a tangent to this class because I will be teaching something that is still very useful in signals and systems, which is actually generalized function. Now, let's talk about common generalized function. Generalized functions. These are functions we already know. Number one, there are three basic common generalized functions that is very common that you are going to be using oftentimes in signals and systems. Number one, we have people call it impulse function, but I love to call it Dirac delta function. Now, impulse function is simply, this is denoted as what? Delta of t. And graphically, it simply means that we only have, it is called delta of t and it's called impulse function because it is only a spike, it's like a spike. And it only happens at what? At 0. This is the signal of interest in signals and systems. Because it actually is very easy to get the response to a system by supplying an impulse function. And oftentimes, engineers generally use it you can actually use it to get the transfer function of a system, that is the whole thing that is happening in the black box of the system, if you actually supply what? A Dirac delta function, or you call it the impulse function. Another function that is of interest and that is commonly used is unit step function. Some people call it if side functions. Now, in a unit step function is just like, I want to believe that someone who is taking the signals and system as a course must have had some mathematical background, on some mathematical method. So, I was saying unit step function u of t is actually something we can call a piecewise function. Mathematics actually believe this is actually a piecewise function. That is, if you have u of t, it is 1 when t is greater than or equals to 0, and it is 0 otherwise. That is to say, I can actually say that my unit step function is 1 from 0 to this place. So this is u of t. So and it is 0 otherwise. So this is a unit step function. Another common generalized function that is of interest is a ramp functions. This is called a ramp, and it is denoted as tu of t. What this simply means is tu of t is equals to, you can also represent it using what? Your piecewise function by saying it is t when the time is greater than what? Is greater than 0, and is greater than or equals to 0, and it is 0 otherwise. Now, this is the part where I will tell you that if you really want me to continue doing this YouTube video, click subscribe and do like the video so that I can continue. That can serve as a motivation to tell me that someone is actually, and please do me a favor, also comment so that I can know what to improve on in this very video. Just so that the video can be better. And please subscribe, like, comment. So tu of t in this case. Now let's go back to tu of t. This is t greater than 0. Now I want to create something here, which is actually that sometimes if there is something we call what I can call unilateral function. by unilateral function. What I mean by unilateral function are functions that start from 0 to infinity. So functions that start now, unilateral function, and we have unilateral function, we have bilateral function. If I have a function, say x of t, if I have a function y of t, and I have something like this, integral minus integral x of t. This y of t is a bilateral function because I'm integrating from minus infinity to infinity. But a unilateral function is y of t is equals to what? Integral 0x of t. So I'm starting from 0 to what? Infinity. This is a unilateral function. So I'm saying something on unilateral function. Now, if you look at this impulse, unit, and ramp function, if we just take them as unilateral, if we take the unilateral function part of them, we can actually create what a connection between impulse, unit, and ramp. And this is how we'll go about it. If you integrate, we can say our unit step function, if we integrate our delta of t in between infinity to 0, we should get what? dt, we should get a unit step function. And the same way, I can get my ramp function, which is tu of t integral from 0 to infinity of my unit step function dt. I'm going to get what? A ramp function. So this is, and you can also do the inverse, which is differential of it. That is, if I differentiate my unit step function, I should get my what? A direct delta function. If I differentiate my ramp function, which is tu of t, I should get a unit step function. These functions are very, very important in signals and in understanding signals and systems. They are commonly used. They will be used in LTIs, in further topics on these signals and systems, like LTI and some other topics that will be common, or some other topics that we will still treat. So please, if you want me to continue doing the video, I'll say it again. Like, subscribe, comment. Any comment is welcome. Either constructive, either destructive criticism is okay. We'll read it, we'll improve on that. So now we'll move on towards power and energy signal.